Okay, so we are on our last now new section here, section 7.2, quadratic forms. And the matrices in chapter 7 are symmetric matrices. Okay, they are symmetric matrices. And actually, in chapter 7, we don't have time to get to it, unfortunately, but there are sections on constrained optimization and singular value decomposition. And then section 7.5 deals with applications to image processing and statistics. So it's a very nice applied section. So you may, at some point, while you have the ebook, might want to look ahead in chapter 7. I mean, on your own after your final exam, it's very interesting material. But all right, let's concentrate on section 7.2. So we talk about quadratic forms, and the book comments that quadratic forms, I'll highlight this here, quadratic forms occur frequently in applications of linear algebra to engineering, design criteria, optimization, and signal processing as output noise power. And then it also mentions that it comes up in physics, okay, in regards to potential and kinetic energy, differential geometry, economics as utility functions. That's actually talked about in section 7.4, and then in statistics, and I've seen that in my own work. So quadratic forms are something that it's a concept that's important for you to see. And let's go ahead and talk about what it is. So, okay, what is a quadratic form? Well, a quadratic form on n-dimensional space is a function q. It's a function q whose value at a vector x can be computed by the expression x transpose times a times x. X transpose times a times x. So let me just go to the whiteboard real quick here. All right. So quadratic form is x transpose times a times x. Okay, and remember, we are assuming here that the matrix A is symmetric. So A is a square matrix. It's symmetric, which means it is orthogonally diagonalizable. And the vector x is an n by 1. So x transpose would be a 1 by n. So when you compute a quadratic form, you're just getting a, well, you're getting a function because if it's a 1 by 1, right? That's a quadratic form. Now, they have a nice example. I mean, there's some good examples in the book. So let's go here. Let's look a little bit at the book, at these nice examples. Okay, so example 1, they give here two symmetric matrices, A and B, and you see there for part A, they compute x transpose A x, where that matrix just has a 4 and a 3 on the diagonal. You see here, this matrix here, it's a diagonal matrix. And when you do the quadratic form, you get 4x1 squared plus 3x2 squared. Now let's compare that with the matrix in B. Okay, the matrix in B. So obviously they're doing matrix multiplication, right? To get they take the matrix A and multiply it by the vector x, and then they take that vector and pre-multiply it by x transpose. If you do X transpose A times X, if you do that one, okay, if you do that one, here's the matrix here. And this matrix in part B is not a diagonal matrix. There are non-zero entries off of the diagonal. And so when you do the matrix multiplication, you end up with an expression, a quadratic form expression, that has I want to say it the right way, it has an x1, x2 term. That's called a cross product term. Okay, so the presence, okay, of that is due to the -2 off the diagonal entries. So hold on here, let me just, the first matrix where you had a strictly diagonal matrix, there was no cross product term. But when you have a matrix, symmetric matrix, say, that has non-zero entries off the diagonal, you are going to get you're going to get a quadratic form that has cross products. So, okay, so let's go. Well, are there any questions on that before I move forward? Okay, then let us move forward here. So example 2 here says, okay, for this vector x, they give you the quadratic form. And they want you to write the quadratic form as x transpose times A times x. Well, that means you have to identify what the matrix A is. You have to identify what the matrix A is. It's going to be a 3 by 3, and it has to be a symmetric matrix. And they write out the matrix A here. And notice along the diagonal, you have a 5, 3, and a 2. Those are the coefficients above in example 2 of x1 squared, x2 squared, and x3 squared. Okay, so the non-cross product terms in the quadratic form, the coefficients are going to be the diagonal of that matrix A. But now you have to figure out the matrix A so you get the cross product terms. You have a -1, x1, x2, and an 8, x2, x3. So x1, x2, you can think of that cross product term. How would we get that? Well, we have to put a number in the first row, second column. Okay, hold on. Yeah, that's right. And they put a -0.5. But because the matrix A is a symmetric matrix, you have to put a -0.5 in the second row, first column. Okay, so I'm focusing here. Hold on, here, here, and here. Okay, now let's focus on the next cross product, which is 8, x2, x3. There's an 8 here, and let's see, x2, x3, second row, third column, they put a 4 here, and they put a 4 here. Can you relate the values -0.5 and 4 to the coefficients of the cross product terms in that quadratic form? Okay, Mikhail, how are they getting -0.5? How are they getting 4? What's sort of the interesting thing you observe? That's right. That's right. And the -0.5 you notice that's 1/2 of -1, right? And the 4 in that matrix A is 1/2 of 8. Do you see that? So if you ever want to get the off-diagonal entries, just take the coefficients of your cross product terms and divide them by 2, and those will be your numbers. Okay, that will work. Okay, so let's see here. Suppose Suppose you had this. Let me go to the whiteboard. Okay, so suppose that your quadratic form were equal to 4x1 squared minus 9x2 squared plus 3x3 squared minus 4x1 x2 plus 10x1 x3 plus 12 x2 x3. Okay, this here is equal to x transpose A times x. A is 3 by 3, x is a 3 by 1, and x is a 1 by 3. Okay, very good. I appreciate that's kind of you, Jake, for Cameron. Appreciate that. So the matrix A, okay, along the diagonal we have, okay, Mikhail, 4, -9, and 3. What are these two entries here going to be? The entry in the first row, second column, and the entry in the second row, first column. What term do we look at here? What term do we look at? Which cross product term? Is it the x1, x2, the x1, x3, or the x2, x3? Well, this entry is in the first row, second column. So I mean, it helps me to think, okay, x1, x2. The coefficient's -4, so we're going to have a -2 here, and we're going to have a -2 here. What about these entries here? Maybe I'll put them in green. What about these entries here? First row, third column, third row, first column. What term do we look at above? Which cross product term? You have 2 to choose from. Well, you're in the first row, third column, so x1, x3. What numbers are going to go here? You have to look at the 10 and do what with the 10? Take the 10 and divide it by okay. Yeah, take the 10 and divide it by 2. That's right. So you have a 5 and a 5. What numbers are going to go here? Second row, third column, third row, second column. Well, we're going to look at this last term with x2, x3. Take 12, divide it by 2, and you'll get 6 and 6. So that's how you identify the matrix A of the quadratic form. That's the, and it will always work, class. It will always work. Okay, are there any questions so far? It is cool and fun. I agree, Michaela. I agree. All right. Well, let's go back to the book now. Let's go back to the book. I don't know if maybe you ever did this in school, but something like this, okay, in a quadratic form like this, would actually be like, it would look like a, well, it'll be, I want to be a little careful how I phrase things. Let me go to the book here. We want to do a change of variables. So remember, we don't like these cross product terms in general. They come up, but if we can find a way to rewrite the quadratic form using a change of variable, and then the quadratic form, the new quadratic form, has no cross product terms, but it's equivalent to the old quadratic form, this would be a wonderful thing. And we can actually do that. Okay, we can actually do that because what we can do is make what's called a change of variable in a quadratic form. Okay, remember calculus 2 when you did changes of variables, how that made the integration easier? We called that substitution, calculus 2, right? Substitution. Well, we can make changes of variables here. Okay, remember we have a symmetric matrix. We have a symmetric, well, I want to be careful here. So if you have x equal to p times a vector y, where p is an invertible matrix, that's a change of variable. You're going from the matrix, the vector x, to the vector y. And what connects the vectors x and y is that x equals p times y. Okay. And note, very, very interestingly, they comment here that here the vector y, here the vector y is actually the coordinate vector of x relative to the basis determined by the columns of P. And that's absolutely true. Absolutely true. So, okay. Now, if we have a quadratic form, if we let x equals p times y, it's very helpful because, again, with the quadratic form, the matrix A, remember, is symmetric. Okay, the matrix A is symmetric. And it turns out that if you take x transpose times A times x, when you work it all out, okay, the properties of transposes there, I'm looking at that formula 2 now. I'm looking at formula 2. The transpose of a product is the product of the transposes in reverse order. And so you're able to write x transpose times A times x as y transpose times p transpose AP times y. Well, it turns out p transpose times AP is a diagonal matrix. It turns out that it is a diagonal matrix. Okay, and that makes sense. And I'm gonna show you why here. I'm gonna show you why. They say, so we're assuming P, by the way, now is an orthogonal matrix. We know for symmetric matrices they can be orthogonally diagonalized. That means you can find a matrix P that consists of orthonormal eigenvectors, right, for the matrix A. And remember here that you learned, I'll go to the whiteboard for a moment here. You learned in section 7.1 that when you orthogonally diagonalize a matrix, you orthogonally diagonalize a matrix. Okay, so again, you know, A symmetric, then A equals P times D times P transpose. That's orthogonal diagonalization. We can find the matrices, the matrix P and that diagonal matrix D, which consists of the eigenvalues of A. We can find that. Guaranteed, right? We can find that. That's what makes symmetric matrices another nice thing about them. When we learned about just regular diagonalization back in section 5.3, okay, in 5.3, not all the matrices you had could be diagonalized, right? But if you have a symmetric matrix, it can be diagonalized, and in fact, you can orthogonally diagonalize it. But look at what we can do here. We can take A equals P times D times P transpose, and we can left multiply that equation by P transpose. We can do that. We can certainly do that. And what's P transpose times P? You know, being that P is orthogonal, an orthogonal matrix, what's P transpose? Orthogonal. That's right. It's the identity matrix. Hold on, I got to spell orthogonal right. Orthogonal. Well, yeah, I have P too close, don't I? P is too close here. There we go. P is orthogonal. That means P transpose is the inverse of P. No problem. So now we have that P transpose times A is equal to D times P transpose. But if we take that and right multiply by P on both sides, P transpose times P is also the identity. So therefore, you have that P transpose times A times P is this diagonal matrix, right? Because you have the identity here. The identity times matrix D is D. And so you see the matrix D is P transpose times A times P. And that's a diagonal matrix. So whenever you see P transpose times A times P, and A is a symmetric matrix, that product will be a diagonal matrix. Okay, and so if we go back to our book here, back to here, the quadratic form, and maybe I will unhighlight a few things here. The quadratic form X transpose times A times X will equal Y transpose times that diagonal matrix, P transpose AP, times the vector y. So this is basically you have a quadratic form now with no cross product term. And this is called the principal axes theorem. Principal axes theorem is here, theorem 4. So if you have a symmetric matrix, you can make that change of variable, x, if you say, hey, let x equals p times y. Now, obviously, what's the matrix P? Oh, yeah, that's the orthogonal matrix that whose columns are the orthonormal eigenvectors of the matrix A, right? Well, I want to be careful. It's the matrix P is an orthogonal basis for the matrix A, and those vectors are orthonormal too. That's probably a better way to phrase it. But the point is, we can transform that ugly quadratic form into a quadratic form, y transpose d times y, with no cross product term. That's called the principal axes theorem. Okay, that's what that's called. So in terms of geometry, it helps to have a geometric view of this. It really helps a lot. So I'm not going to get too deep into the weeds, but they have some figures here. They have some figures. And looking at figure 3, do you see how you have an ellipse there? You see how you have in figure 3? I don't know if you maybe did this in high school. You're used to how many recall in high school? Let's focus on the ellipse, like figure 2. An ellipse in standard form with intercepts, x-intercepts at A and y-intercepts at plus, x-intercepts at plus or minus A, y-intercepts at plus or minus B. The standard form is given there. X1 squared over A squared plus y, x2 squared over B squared equals 1. Right? You recall that from, and right, that's right, Mikhail. If A and B equals 1, you have a circle. So that was an ellipse. Now, but what happens is when you have an ellipse that's oblique, like you have here. I don't know if you saw this. I remember when I learned about those in oblique ellipses in high school. What we had to do to graph them was just find a ton of points, basically, and they're very hard to graph, right? They're very hard to graph. But if you can adjust the axes so that the axes are y1 and y2, like they show in the page, like they show in the picture there, you see the x1, x2 axes in figure 3A, the ellipse. The x1, x2 axes are not convenient axes to graph that ellipse. The convenient axes to use are the y1 and the y2 axes. Those are the convenient axes to use. And so we can get that by we can rewrite the quadratic form more easily with the variables y1 and y2. Okay, so let me show you. Do you see what I'm trying to say here? We're trying to, we want to be able to visualize like this quadratic form, which is in figure 3A, which is 5 times x1 squared minus 4x1 x2 plus 5x2 squared. We set that quadratic form equal to 48. That creates these points on an ellipse. But the x1 and x2 axes are not convenient frames of reference axes for this ellipse. It's better to have the axes y1 and y2. That's better. Okay, I mean, basically you have the intercepts are very easy to see if we use y1 and y2 axes. Give me a thumbs up if you're okay with that, because Give me a thumbs up. Okay, David. All right, Marcella. And it takes a little time to feel comfortable, but all right. Well, let's do this. Let's do a process here. Let's do an example. We're going to work with this ellipse. Very good, Mikhail. We're going to work with this ellipse here. So let's get this example done before we go on break. Thank you, Jacob. Very good. Okay, take a moment to copy this example down. And this example, this ellipse deals with the ellipse that we saw in Figure 3, Part A from Section 7.2. Let me give you a moment to copy this. Mikhail, we need to find the matrix P and the matrix D, yes. And the matrix P, we're going to look for the eigenvectors of the matrix A. Well, first we have to find the matrix A. Okay, so quadratic form here. Hold on, let me rephrase it. Right, A first. Okay, so hold on, I think I need smaller font. Okay, so Q of X is going to equal x1, x2 times the matrix A times x1, x2. This is the vector x. This is X transpose. This is the matrix A. What goes on the diagonal? So, and I'll tell you this, so what we're saying here is on the left here, on the left, this equals the quadratic form. Okay, Mikhail, hold on. So Mikhail's saying on the diagonal, we have a 5 and a 5. That makes sense because those are the coefficients of x1 and x2, x1 squared, x2 squared. And what's going to go, and I think, Mikhail, you have it right, but let's just, what goes on the off diagonal? What numbers go on the off diagonal here? Well, we look at -4. What do we do with -4? Do you remember? Got to get this number, got to get this number. Take the -4. Mikhail, can you say what we do? We half it. That's right. That's right. So this gives us -2 and -2. So now we have our matrix A. And what we're going to do now is we're in section 7.2. You can use MATLAB for section 7.2. We're going to put this matrix A into MATLAB. Okay, and you know the command P comma D equals I of symmetric of A, right? We're going to put that in. And we're going to get our eigenvalues and eigenvectors for the matrix A. So, okay, here we go. So we have a symmetric matrix. With MATLAB, we get our eigenvalues and eigenvectors. And now we can construct the matrix D that has eigenvalues 3 and 7. And we can construct our orthogonal matrix P. Notice these eigenvectors are orthogonal, right? They're orthogonal, those two eigenvectors, V1 and V2, because they are eigenvectors from two different eigenspaces. And so the eigenvectors, when we have a symmetric matrix, eigenvectors from different eigenspaces are mutually orthogonal. We proved that in our last class. Let me see, Mikhail's saying, I'm not quite sure, Mikhail, what your question. I mean, I assume you're looking at MATLAB.
No, I mean, is there a common name to call eigenvectors and eigenvalues without needing to say eigenvectors and eigenvalues? Like just one word for both of them.
Not that I'm aware of. I'll tell you that. Not that I'm aware of.
So we just call them eigenvectors and eigenvalues, and that's it, right?
That's correct. Normally
Okay.
we'll say eigenvectors corresponding to their eigenvalues. But yeah, that's right.
Okay, that makes sense. Okay, thank you.
All right. Very good question. And so what we do is our matrix P. So notice MATLAB will give us eigenvectors, but they're not of unit length. So we have to adjust the eigenvectors so they're of unit length. And then A will equal P times D times P transpose. And now we're going to use this change of variables. Now we can make this change of variables since we know what matrix P is. And just a reminder that D, the matrix D, is equal to P transpose times A times P. Okay, just a reminder. Okay, so are there any questions before we move forward here? Okay, well now let's go ahead and let's make this change of variables so we can rewrite our quadratic form. So on the next page here, okay, the 5x1 squared minus 4x1x2 plus 5x2 squared, that's equivalent to the quadratic form x transpose A of x. Okay, and we know what that matrix A is. But I'm going to write that now. I'm gonna make the change of variable. I'm going to say let x, let x equals p times a vector y. We can do that. And so because x transpose ax equals y transpose times the diagonal matrix D times y, the diagonal matrix D is just the eigenvalues, right? The matrix of the diagonal matrix with eigenvalues. You see, now we don't have any cross product terms here. And so what we end up getting is right. I mean, what we end up getting, we have, well, the ellipsoid, this oblique ellipse, okay, with respect to the x1, x2 axes, is equivalent to the ellipse 3y1 squared plus 7y2 squared equals 48, which is a non-oblique ellipse relative to the y1 and y2 axes. Or think of it this way. The oblique ellipse 5x1 squared minus 4x1 x2 plus 5x2 squared equals 48 with respect to the x1, x2 coordinates is equivalent to the much simpler elliptical equation 3y1 squared plus 7y2 squared equals 48 with respect to the y1 and y2 coordinates. And the y1, y2 coordinates are related to the x coordinates through what I've written below here. So any y1, y2 coordinate is a linear combination of those eigenvectors for the matrix A, the orthogonal eigenvectors. But there's actually a nicer way to look at this, because what kind of matrix is this matrix P transpose? If you think back to matrices where you transformation matrices, think back to like section 2.7. Yes, that's right, Mikhail. It is a rotation matrix. So what are we doing? What are we really doing here? What are we doing? All right. What we're doing is this. Well, first of all, is everybody ready to go to the next page? Give me a thumbs up if you're ready. Okay, Mikhail's good. David's good, wonderful. Marcella's good, excellent. And Jacob? Okay, okay. Fatima, how are you? Are you good? Wonderful. Zishan, are you good? Fatima's good. Yasin, are you good? Good, good. All right. Let me show you now. This is really, truly cool what you're going to see. Here's what's going on. So the matrix P transpose yes, yes. The matrix P transpose is a rotation matrix. And if you have to go back into chapter 2, but I mean, generally what we did to figure out our transformation matrices, well, I want to say this the right way. When you first learned about transformations, this was back actually in chapter 1. If you look at section 1.9, in example 3, they show a transformation matrix. Okay, and the transformation matrix is of this form. It's of this form here. And this corresponds to rotating a coordinate or a vector 45 degrees counterclockwise. So what you're doing here, if you think of, like in the picture there, if you think of the point like, think of the point 1, 0. Okay, think of the point 1, 0. If you were to rotate the point 1, 0, 45 degrees counterclockwise, that's going to get you to the eigenvector 1 root 2 negative 1 root 2. That'll get you to that eigenvector. And if you were to rotate the coordinate 0, 1, which is on the x2 axis, if you were to rotate that 45 degrees, that would get you to the coordinate 1 root 2 1 root 2, which is the other eigenvector. So essentially what you're doing is you're making a change of axes so that it's easier to graph this ellipse. That's what this change of variables is doing for you. And the ellipse, okay, 3y1 squared plus 7y2 squared equals 48. In standard form, it's written this way. And so you can identify the y1 intercepts as 4, 0 and negative 4, 0, and the y2 intercepts as 0 plus or minus root 48 over 7. So if on the y1 axis, okay, we just, these are the y1 intercepts. If you put 4, 0 here and negative 4, 0 there, after all, y1 is 4, negative 4. And then on the y2 axis, if you put plus or minus root 48 over 7, okay, that equals, and I know you're copying, but I'm just sort of, you know, my thoughts are very clear, and I'm trying to, you know, share them with you. Square root of 48/7 is about 2.6. So see, when you do the change of variable, you get an ellipse that's easy to graph. You just graph that ellipse on the y1, y2 axes. How do you get the y1, y2 axes? Take the x1, x2 axes and rotate them 45 degrees counterclockwise. So to do that, you know, you just take the E1, the E1, which is 1, 0, E1 vector, and rotate it 45 degrees. And then the E2 vector, which is 0, 1, rotate that 45 degrees. And then that tells you that tells you what your new axes are. And that's the figure 3 in the textbook. Figure 3 in section, figure 3A in section 7.2. Okay, we're almost done, but are there any questions here? And I do appreciate your patience. I mean, I know normally I get you your break sooner, but we're almost done here, and I want to try to give you some time here to work in your groups on your MATLAB assignments. So we're just trying to get this done. But how many think this is really absolutely fascinating? This, I mean, what you're learning here. Okay, Mikhail's liking it. Cameron's liking it. Wonderful. Yes, yes, it is pretty cool, and um, tremendously applicable too. I'm sure many of you are going to take like a matrix class, another class, like the next class after this, when you go like for you transfer to your four-year institutions, and you know you're going to have a good foundation here. Okay. Now, one thing that they talk about in the book, now we have a geometric understanding of what we know what a quadratic form, in terms of like an ellipse, we know what a quadratic form is, and we understand through a change of variable we can take a quadratic form with cross product terms and turn it into a quadratic form with no cross product terms. And this makes it helpful in understanding the quadratic form and graphically. There is a further idea here where you can classify quadratic forms. So quadratic forms, remember, are functions of they are, I mean, the eigenvalues play a role in the quadratic forms. And remember, the eigenvalues in a quadratic form are the coefficients of x1 squared, x2 squared, x3 squared, and so forth. So let me show you something here in the book. Where they classify quadratic forms. Okay, hopefully we're good here. Let's head to the book. No questions. All right. Here we are in the book. Figure 4. They talk about, in this section here, classifying quadratic forms. And they have a picture here where they have some quadratic forms where z equals the quadratic form. And notice that in part A, the paraboloid, which is graphically what the quadratic form is, that paraboloid goes up. And both coefficients of x1 squared and x2 squared are positive. Okay, the next quadratic form has one positive eigenvalue, one positive coefficient. Remember, in quadratic forms, the coefficients of x1 squared, x2 squared, x3 squared, and so forth are the eigenvalues. Now in part C, yeah, that's a hyperbolic paraboloid. That's right, Mikhail. And one of the eigenvalues is positive, one of them is negative. And in part D, both eigenvalues, -3 and -7, they're both negative. So you see, we can classify quadratic forms as being positive definite, negative definite, or indefinite, based on the quadratic form where the z values are. Okay, so those are definitions of quadratic forms. And you have pictures. So figure 4a, that quadratic form is positive definite, because that quadratic form is always greater than 0. All the z coordinates are positive. On the other hand, for D, the quadratic form there is negative definite for D, because the quadratic form, all the values of the quadratic form are entirely negative. Okay, entirely negative. Okay, because Z is equal to the quadratic form, and the Z coordinates are negative. That's why that in D, that paraboloid is entirely below the x1, x2 plane. All the Z coordinates are negative. Finally, quadratic form is indefinite if the quadratic form assumes both positive and negative values. That would go with number C. Okay, so part of the surface is above the x1, x2 plane, part of the surface is below the x1, x2 plane. Okay, and then you even have other classifications, positive semi-definite, negative semi-definite. But what I want to focus here finally is on Theorem 5. Theorem 5, when is a quadratic form positive definite? When is it negative definite? When is it indefinite? It depends on the eigenvalues, because again, those eigenvalues are the coefficients of the squared variables. And so, you know, in your homework for section 7.2, which is due on Friday, you know, you'll have questions where you're asked, is this quadratic form positive definite, negative definite, or indefinite? So that's quadratic forms. That is the concept of quadratic forms. And I'm glad you like it. It's a nice section to end with for our course. You know, and I think it's great. I think it's great, and I'm glad you're liking it. Are there any questions before I stop our recording here for section 7.2? Okay, Cameron's good. Who's give me a thumbs up if you're good. Cameron's good. I always like thumbs up. And our Yasin's good, excellent. Marcella's good, Jacob's good, Belen, wonderful. Everybody's pretty good here. All right, let me put a little. Wait, there's somebody else here. Mikhail's good, excellent. All right, I'll stop the recording.